This is the complete setup for the experiment, which includes a function generator, amplifier, oscilloscope and a shaker. It includes a 4-meter long concrete beam with 19 sensors embedded at the top and 19 at the bottom. Now if we take a closer look of this beam, we can see the embedded sensors flashing at the top. This is the typical sensor which is embedded inside the concrete beam. These are the connectors coming out of the sensor. This one is for the top sensor and this one is for the bottom sensor. I have given a notch at the 1/3 length of the beam. This is to create a damage condition. We will be creating 3 levels of damage, in which first level will be chipping off the concrete. In the second level we will curtail the 50% of the reinforcement, and in the third level we will curtail 100% reinforcement. This is an inertial type shaker developed in our lab. It has been transformed from a contact type shaker. The benefit of this inertial type shaker is that we can enhance the force transmitted to the beam, which was earlier 98 newtons in case of contact type shaker and 108 newtons in the inertial type shaker. Now the principle on which this shaker is working is that the vibration of this inertial mass, which is the plate in this case, is transferred to the beam via these 4 springs. The additional mass can be increased or decreased by adding or removing these extra plates developed for additional masses. This is the function generator and this is an amplifier. This function generator gives an electrical signal which is amplified by this amplifier and then further transferred to the shaker, which gets converted into mechanical signal. Now before starting this amplifier, some signal should be given to it. We will switch on the function generator, give a noise signal here and switch on the output. Now we will start this amplifier. As soon as we see a number 1920 here, we will press this button. Now it's ready to use. Next step is to give us sine wave in this function generator. For that we will switch off the output. These are the different type of electrical signals which can be given using this function generator. We will give a sine wave. So we will give a 10 volts peak to peak voltage and a frequency of 16 Hertz. Now if we press a button graph, we can see the sine wave generated by this function generator with a amplitude of plus minus 5 volts and a frequency of 16 Hertz. Switch on this output and slowly increase the gain. Make sure this number doesn't go beyond 2. If you connect any of the sensor with the oscilloscope, we can see a sine wave signal when I switch on the output, which dies down as soon as I switch off the output. Next step is to measure the energy or power generated by the sensor. For this we have fabricated a circuit in our lab. Since the current is very small across the sensor, so it's very difficult to measure the current. So we have fabricated this circuit using which we will be measuring the voltage across the resistor R1 and then calculating the current. Here PZT patch is attached and here output across resistor R1 is As soon measured. As I switch on the output, this is the voltage signal which is seen across the resistor R1. After quantification of the energy generated by the PZT patch, next step is to store that energy. For that we have fabricated a full wave bridge rectifier circuit. We have connected the PZT patch here and we are measuring the voltage across this capacitor. Here yellow line represents the input voltage across the PZT patch and blue line represents the capacitor voltage. Now when I switch on the output, we can see the increase in the input voltage across the PZT patch, and we can also observe the charging of the capacitor. When I switch off the output, that capacitor gets discharged and the input signal dies down. An 85933 circuit, which is an alternative circuit for LCR meter. For starting this circuit, it has to be first calibrated with a 200 kilo ohm resistor. So we'll connect this resistor with the circuit and we'll give a start frequency of 50 kilohertz and a delta frequency of 200 hertz. Number of increments are okay, and we'll give internal oscillator, then start the program device registers, okay, calculate gain factor, okay, then measure the temperature, enable the theoretical calibration profile and start sweep. Now this blue line is the calibration curve and black is the actual reading, so they should be very close to each other. Calibration part is done, so we will remove this resistor and will attach the PZT patch. Measure the temperature of the PZT patch, start the sweep, and now we can download the data in the Excel file. This real and imaginary, these are the useful part of the data. Real part represents the resistance and imaginary is the reactance. So we can calculate the conductance and susceptance by dividing the real and the imaginary values with the amplitude. We are planning to charge these batteries using this LTC demo circuit board designed specially for piezoelectric sensors. The input voltage required by this demo circuit board is 4.3 volts, but the voltage level generated by the PZT patch is very small, so we are working to enhance those voltage levels. When we'll achieve the threshold values, we won't be using these input batteries across this demo circuit board, so we can achieve a voltage of 3.6 volts and a current of 100 milliampere using this LTC demo circuit board.